Hey student, welcome back to your physics teacher. Today I'm going to be showing you section 11.8 from the Nelson textbook. We're going to be looking at how different resistors are set up in series, parallel, and mixed configurations, and how we can get the equivalent resistor. So we're going to be looking at a couple different examples, so let's get started with question number 5. Question number 5 reads, what is the equivalent resistance of the following circuits? Each resistor has resistance of 12 ohms. Now, one good strategy that you can take as a beginner level is to consider only 2 resistors at a time and see how those are set up, and then find the equivalent resistance from those 2. And as you develop more and more in this unit, you might want to take on 3 or 4 at a time depending on the circuit that you're working with. So again, as a beginner, start off with only considering 2, then you want to consider 3 or more to show how more advanced you have become. So in this diagram here, we have resistors R1 and R2. Those 2 are set up in series, so you want to draw the equivalent resistor. So this circuit can be represented in its equivalent way by considering R1 and R2 in series. So this new resistor up at the top, we're going to call that R12. So that's one good strategy to use as well. So you notice how the index number 1 and 2 is considering the equivalent of resistor 1 and resistor 2. So on the side here, you might want to write R1 and R2 in series. And because they are in series, if you remember the rules that we derived, we just simply need to add the 2 resistors together. So in other words, R1 plus R2. And each one is 12 ohms, so it's going to be 12 plus 12, giving us 24 ohms. Now, we didn't change anything from the other 2 resistors, so we're going to carry those along with us. So we're going to keep labeling them as R3 and R4. And we're going to repeat the process. So we're going to try to find another equivalent circuit by considering 2 resistors at a time. Now, in this case, I'm going to consider the bottom 2. So I'm going to consider resistor 3 and 4. So by considering resistor 3 and 4, notice that those 2 are actually connected in series. So we have R3 and R4 in series. So we're going to use the rules of adding resistors in series, which is just simply add them together. So R34, which represents the equivalent resistance when you add up resistance due to 3 plus resistance due to 4. And once again, all the resistance of each individual resistor was 12. So we can put 12 plus 12, which once again gives us 24 ohms. So let's draw what the equivalent resistor will look like. So the one from before, R12, and now considering R34 as a single resistor. And we're going to repeat the process. So now we're going to consider 2 resistors connected at a time, and the only 2 that we have left over are resistor R12 and resistor R34. And we notice that these 2 are actually connected in series, so we're going to use the same strategy that we've been using from before. So let's draw the equivalent circuit. So now we'll just have a single resistor. And this single resistor is the total resistance. So we could write as R total. Now another way that you might have seen it in other books, they call it the R equivalent. So the equivalent resistance of the whole circuit. So this will be the same thing as adding the two resistors from before, which was R12 plus R34. And we're doing this because R12 and R34 are connected in series. Now, yet another way of representing the total resistance in the circuit, i.e. equivalent resistance, is to use the subscripts that we've been having from before. So this new equivalent resistance considers R12 and 34 combined. So that's why I like to put the numbers instead. You could try to use this strategy too. You're going to find it more helpful than writing R equivalent. So this way you make sure that you use all of the resistors in the circuit. And the resistance of R12 was 24 and 34 was 24. Let's add those together. We get 48 ohms. So that's what this question was asking us to find. So if we go back, they were asking you for the equivalent resistance, which is the same thing as the total resistance in the circuit, which is what you do by considering all of the resistors in the circuit. So we get that the total resistance is 48 ohms. Now, maybe that was a bit too much for you for your first time. So stay tuned. Please hit like if you're enjoying it so far. That way you're going to help me grow my channel. And this way I'm going to show you more examples too, because I get encouraged to keep making the videos. So let's look at example B. It's the same thing as before. They want us to find the equivalent resistance in the circuit. Now the strategy that we said from before is to consider two resistors at a time. So I'm going to consider R1 and R4 because these two are connected in series. So if you see at the beginning from the power source, if we follow the current is going to split at this junction here. So we have a parallel circuit. So in this parallel circuit there are two branches. So we wouldn't want to consider resistance 1 and resistance 2. Because that's going to make our life more complicated because we have other things to consider. So it is better to consider one branch at a time when you have a parallel circuit. So that's why I'm going to consider the equivalent resistance of considering R1 and R4 because these two are connected in series. So first, let's draw the equivalent circuit. In this branch, we're going to find the equivalent resistance, which is R14. We haven't done anything with the other branch for now, so let's keep it as it is. And because resistance R14 is connected in series, all we have to do is just simply add the two together. So R14 is going to be the resistance of 1 plus the resistance of 4. And once again, the resistance of each resistor is 12 ohms. So 12 plus 12, which gives us 24 ohms. Now we continue with this strategy again. We consider two resistors at a time. But once again, you don't want to be considering one branch and not the other one. Wait, let me say that again. You want to fully consider one branch at a time, which we did. Then if we look at the other branch, we have two resistors, R2 and R3. Those two are connected in series. So we're going to first find the resistance due to R2 and R3. So let's draw the equivalent circuit, and then we're going to find the actual number. Okay, so now we're noticing that we have resistor 2 and 3 are connected in series. Because they're connected in series, the equivalent resistance due to those two resistors is just the sum of R2 plus R3, which once again gives us 24 ohms. And with circuits, you just need to continue strategy and keep simplifying it until you get one equivalent resistor. Now, when we consider the two resistors left here, we notice that these two are actually connected in parallel. So let's draw the equivalent circuit, and then we're going to analyze to find the resistance. You know, saying resistance, resistor, continuously, I might get tongue twisted. So if I make a little mistake, make sure you leave a comment, and that way I could help others not get lost in my explanation. So again, it does get a bit tongue twisting, so I apologize if I messed that up at one point. So this new equivalent resistance is due to R14 and 23, which is why I like to put the numbers there, so I consider all of the resistors. But our book calls it R total, so the total resistance in the circuit. Or once again, we call it the equivalent resistance. And because the other two were added in parallel, we need to use the formula that we derived for adding resistance in parallel. So it's going to be the reciprocal formula. So R1 over R4, 1423 is 1 over R14 plus 1 over R23. Okay, let's put in the values. We had a 24 resistance for each of these, which is adding up some fractions. It'll be 2 over 24, which simplifies to 1 over 12. So this means that the total resistance is going to equal to 12 ohms. Now the last step, maybe I should mention it to you because your math might not be so great, so I'm going to be kind. One way to approach it is to do cross multiplication, which will mean 12 times 1, which is 12, R total times 1, which would just be R total. So that's where I got the 12 ohms from, if you got a bit lost. So again, I'm being extra nice to you, so make sure you hit a thumbs up because you have to be extra nice to me too. Whoa, where's my next question? Okay, so for question 5, there's 2 more. But hopefully now you're gaining more confidence, and as you may suspect, the challenge is going to get more and more as we go along in this video, so you want to stay tuned and look at the more challenging questions, right? Because that's what's always going to come up on the test. And because they're more challenging, if we were to use our strategy of only considering 2 resistors at a time, it will take up a lot of space. So now we're getting more clever. And instead, we're going to consider more than 2 resistors at a time. So let me show you in this new strategy that we're going to use. So if we start following the current from the terminal, first it goes through resistance 1, then the current splits, and then we have 2 branches. So these 2 are set up in parallel. And it is best to usually simplify the branches first. So notice that for the branch containing R2 and R3, those 2 are connected in series. So let's make a note of that. R2 and R3 in series, which means that the equivalent resistance due to those 2 is going to be the sum of the individual parts. Which is going to be 12 plus 12, which gives us 24 ohms. And now we're going to consider the other branch at a time too, because we're developing a bigger strategy to handle more complex questions. So if you look at R4 and R5, those 2 are connected in series. So we're going to repeat the strategy that we used for the other branch of the circuit. So we have R4 and R5 in series. So to get the equivalent resistance due to those 2, it's going to be the sum. And let's put in our values, which is 12 ohms for each one. And we get 24 ohms as the equivalent of adding R4 and R5 together. And let's now draw our new simplified diagram. So in this simplified diagram, or again equivalent circuit, we didn't do anything with R1, but with the whole parallel branch, we found that it got split into 2, the branch got split, and we analyzed each of the branches to find the equivalent in each of them. So wait, I need to correct my drawing a bit. So at the top branch we found R2, 3, and the bottom branch we found R4 and 5. Now we're going to consider 2 at a time, and those are going to be the ones that are actually connected in parallel. So the 2 branches of this parallel circuit. And notice that because they're connected in parallel, we're going to have to use the formula for resistors in parallel. R2, 3 and R4, 5 in parallel. So that's going to be the complicated formula, right? The reciprocal one. And it's good to use the numbers below so that we keep track of the resistors. So it's R2, 3, 4, 5, which is the sum of 1 over R2, 3 plus 1 over R4, 5. One over 24 plus 1 over 24. Simplifying to 2 over 24, reducing a fraction to 1 over 12. Now, by the same strategy as before, we could do cross multiplication, and we will find that the resistance due to 2, 3, 4, 5 is just 12 ohms. So now that we found the equivalent resistance, let's draw the equivalent circuit. So let's draw it in. Let's label it. So R1, we still haven't done anything with it yet. And now we've taken care of this whole parallel branch to find the equivalent resistance for that branch itself as R2, 3, 4, 5. And you see how much simpler it got now? Now we only have 2 resistors at a time, and these 2 resistors are actually connected in series. So when they're connected in series, the equivalent resistance is just the sum. So let's draw our equivalent circuit. Now this equivalent resistance is R1, 2, 3, 4, 5. That's ensuring that you took care of all the resistors in the question. You could also write it as R total. And because these two were connected in series, all we have to do is just simply add them together. So it'll be the sum of R1 plus R2, 3, 4, 5. So 12 plus 12, which gives us 24 ohms. Good. So you see the strategy. If it was very complicated at the beginning, we consider more than 2 at a time. But ultimately, the best strategy is always considering 2 at a time and to deal with the parallel branch first. Now, hopefully the last question will get more challenging, so you get more out of this video and you'll be better prepared for any other questions that you're going to get in your homework. Alright, so now once again the resistance in each one is 12 ohms. Let's first take care of the parallel branch, and within the branch let's take care of one at a time, or if you're more ambitious, now you can consider more than 2 resistors at a time. That's what we're going to do in this video. So we're going to consider R2 and 3 at a time, and then we're going to consider R4 and 5. And I'm going to go a little bit faster because this looks similar to the one from before. These two are connected in series, so it's just the sum, which will be 12 plus 12, 24 ohms. And considering R4 and 5, which is in series, we're going to add up the 2 resistors, which would be 12 plus 12, once again 24 ohms. And let's draw our equivalent circuit, that way we don't get lost. So let's draw it in. Let's label it R1. The top branch is going to be R2, 3. The bottom branch R4, 5. And now we have a resistor down below, which is R6. So again, let's take care of the parallel branches first. That's a good strategy. So we're going to consider R2 and 3, which are connected in parallel. And because they're connected in parallel, the formula is going to be the reciprocal one. Which is 1 over 24 plus 1 over 24. Adding our fractions, 2 over 24 simplifies to 1 over 12. And we do cross multiplication, and we find that the resistance due to 2, 3, 4, and 5 is going to be 12 ohms. Now let's redraw our equivalent circuit. Label our diagram again. All right, so now it looks more friendly, and although the good strategy is to consider 2 at a time, we could get a bit more ambitious in this case because all three resistors are connected in series, right? We have R1 is connected in series to R2, 3, 4, 5, which is connected in series to R6. So we can get very ambitious and do this in one single step. So we could write our total, the total resistance in the circuit is going to be the sum of R1 plus the sum of R2, 3, 4, 5, well, it sounds strange, plus R6. So the total resistance is going to be 12 plus 12 plus 12. So we're going to have 36 ohms. And just for completeness, let's draw our diagram. So you see, you could consider more than 2 resistors at a time, but then it just depends on your comfort level and making sure that first you try to deal with the parallel branch, because that's going to mess up most of the questions when you're making this, when you're solving these questions. Now stay tuned, because in the next lessons I'm going to be talking about how we can use Ohm's law and Kirchhoff's laws to solve even more complex circuits. Those ones get really complicated, so make sure that you stay tuned and you subscribe to the video so you can watch more.